recording, guys. All right, so we're doing homework solutions. Handout A, page 3 and 4. You're asked to consider the full function 2 sine 3's data. And that's going to be a Rosen curve. Remember, if you have an odd number, odd coefficient of data, then that's the number of petals you have, block 3 petals. And with sine, it's going to be symmetric about theta equals 5 and 2. So that's the length of the petals is determined by the coefficient in front of sine, or the trig function, which is 2. So it goes to the radius of 2. That should make sense. But obviously, most sine is 1. In terms of the orientation, because it's 3, they're going to be separated by 120 degrees, so we're 5 or 2 pi or 3. The best way to kind of figure where it's going to go, it is 3 phase, so it's kind of weird. So if we were to plug in 5 or 2, what's sine 3 pi or 2, guys? So the r is -2. So when you're 5 or 2, you're over here, but because of negative r value, that's why that petal is there. And then you just have to assume the symmetry of about the 5 or 2. And of course, the separation of the petals separated by 120 degrees with 2 pi. So hopefully that kind of makes sense. Like once you have where the first petal is, the rest is kind of pretty easy, right? You do the graph. Of course, you're asked to find starting points. So yeah, just plug in 0, so it's up full. So that's where it actually starts. But look at the graph from the symmetry. We already talked about that negative pi or 2. So in order to do that, you have to do negative r and negative theta. There actually was in the notes, there was a little thingy about, hey, here's where, and by all the fill out notes are in Schoology as well, so you can locate them. But I think at the end of part 2 of the notes, there's a little summary at the end of like how to, yeah, there we go. So in order for testing symmetry, you really need to know this well, right? That's symmetry. So pi or 2 is negative r negative theta. The pole axis is r negative theta, and for pole negative r theta. Yeah, that's how you can test the symmetry. Coming back here again. So there we go. Symmetry about line theta equals pi over 2. Algebra determine the zeros. So just plug in 0 for r, solve for theta. You get every pi over 3, 0, pi over 3, 2 pi over 3, blah, blah, blah. That's when r is 0. So that's when it's touching the we'll be touching the pole for sure. What else we need to say? Yeah, it gets traced twice. Yeah, so another thing that this is why the graphic calculator probably helps. You kind of do this piecemeal. Like let's just graph from 0 to pi over 2 to pi, pi to 2 pi to 2 pi to 3 pi to 2 pi. You kind of like go to the window and like adjust the beta and the max. And kind of do portions of this whole interval. You'll see parts of the graph, and you'll see that it does retrace. There is a retracing that does happen with row curves. So that's kind of what's happening there. And then if we keep moving, algebra determine points where it crosses those places. So again, plug in 0 for theta, plug in pi over 2 for theta, work it out. You get that. But it's also a good idea that just to test other, they're called quadrangles, like basically where the axes are, like 0, pi over 2, pi, 3 pi over 2, and 2 pi. It's good to test those as well, just to get a general idea of where all the points are going to be. So just do more than 0 and pi over 2, do pi, 3 pi over 2, and 2 pi. And then, yeah, this is a little tricky. So I think that's where you put, it's not terribly obvious. I think a lot of it's going to be a little bit of trial and error, to be honest with you. But if you were to play around a little bit with it, like go to the graphic calculator with the video, and kind of see, okay, well, let's check this graph. And the fact that it's 3 curves, right? So you know this is separation of 2 pi over 3. So yeah, see what happens. You go from 2 pi over 3, see what happens. See what happens from 2 pi over 3 to 4 pi over 3. See what happens from 4 pi over 3 to 2 pi. So I kind of urge you to kind of test those things out a little bit. So a lot of those kind of require a little bit of trial and error. To be honest, it's not really algebraic way of thinking about it. So that's what's happening there. For our test on this stuff, it will be calculator allowed. So calculators will be allowed. I haven't figured out exactly how many questions are yet, or how it's actually going to be designed. I'll do that over break. But if I think of some things, I'll put it in Schoology. But by Monday, when we're back from break, I'll tell you guys more. And today should be the last day of the polar unit. I want to get it all done. But we do have a couple of small topics to cover after break, but not for this unit. They'll be after the test. They'll be before finals. Anyway, that's the rest of the answers for that. And then for the other handout, handout B, pages 7 and 8. Here we go. pages 7 and 8. So another rose curve. Now in this case, it's an even number in front of theta, so we expect double the that coefficient, so 8 petals. And 4, if you think about it, so 8 petals, 365, 8 45 degrees, so we're stuck at 45 degrees. You are going to have symmetry about theta equals 0. And if you think about it, you also have 45 degrees, right? 0, 45, 90, 135, 180, 225, 270, 315, and 360, right? Yeah, it's really starting point, so putting 0. So there you go, 0. So that's where you start. You can see where it says start right there. The symmetry, it's definitely symmetric about theta equals and theta equals pi over 2. So you can do both and check them out. Also symmetric about the pole as well. To be symmetric about the pole, you rotate 180, you have to be back to the same orientation as we're originally. It would be, if you rotate 180, back to the same orientation as we're originally. We also got here, determine the zeros, plug in 0 for r, solve for theta. This actually happens every pi over 8, 3 pi over 8, 5 pi over 8, separated by pi over 4. Algebra to determine the points. Again, don't do more than 0 and pi over 2. Do 3 pi over 2, 2 pi and pi. What else is going on here? Okay, this one here is a little funky. It's actually a cotangent that's happening to this one. It's actually a cotangent. Because was that? Or was that part of your notes? Oh, then we're done. Okay, then why was this?
It was on the page. Do question 3.
Okay. That's fine. Don't worry about it then. Oh, you mean on school, just said question 3. Yeah. Oh, then don't worry about it. We're good. But if you did do it, yeah, you graph it, you should be able to see what the symmetry is and then test it out, depending on what kind of symmetry you're seeing there. And then, yeah, just plug in 0 for r, solve for theta. Shouldn't be that hard. So, anyway.
So you want to test all 3 symmetries?
What you do?
No, what you do is graph first. And if you see it has all 3 of those symmetries, then just verify. So if you see all 3, right. If you only see like one,
just do the one that you need to. Right. Okay. All right, guys, let's talk about the notes. Let's keep moving, guys. We got to keep the train moving here. So go to page 21 of the notes. It's the end of the part 3. And I'm going to try to blast through part 4. I think I get all part 4 done. I'd be really happy if we do. We shall see if we do. And then homework will be the rest of the homework packet. Handout C and D is the rest of the homework, which we'll do over break. And I already put the assignment in Schoology as well. All right, let's finish this up here, guys. This is connecting the conics. So what you're told to do in the instructions for part C is to convert the polar to rectangular. So let's do it. And remember what we did last time? We multiplied both sides by the denominator and then kind of got a little creative with the substitution part. So if I do that right now, r2 plus sine theta equals 3. 2r plus r sine theta equals 3. Okay. Now, what should I do next? Bless you. What should I do next, guys? Make that y, yeah. Now, if you want to replace r with root x squared plus y squared, go ahead. Personally, I'd rather square both sides after I move y over. So I would actually, this is just my preference, I would do this. Then square both sides. So you get that. Hopefully that makes sense what I've done so far. And then what would I do about r squared at this point? Yeah, so that way we don't have to deal with radicals, right? So 4x squared plus y squared. I'll take a little break so you guys can get caught up here. Okay, so once you guys get now keep going. Move everything over to one side. So I'll have 4x squared plus 3y squared plus 6y minus 9. I kind of skipped a couple steps. I distributed, move all the terms to the right to the left, combine like terms. So I actually did kind of 3 steps here. Distribute 4y squared minus y goes 3y squared. 9 from right to left comes -9. -6y from right to left comes +6y. I think I've got all that. Yes, so far so good. Okay, this part's ugly. It's not gonna be fun. 4x squared is cool the way it is. I'm gonna factor out 3. and do that. And then 9, actually, I'm going to put it back to the other side. I think I prematurely moved that over. I'm going to push it back to the other side. What should I do next, guys? You got to complete the square, totally. Complete the square. Half of 2 then square is 1. So I have to add 3 here. We're cool so far? Okay. Switch colors for a bit of contrast. 4x squared plus 3 parentheses y plus 1 squared equals 12. Ooh, it comes out really nice. Divide everything by 12. This is lovely. Look at that. It comes out really, really nice. There we go.
So clearly it's an ellipse. Center 0, -1. The major axis is vertical, going 2 up, 2 down. So the major axis is 4. The minor axis go √3 left, √3 right. So the length of the minor axis is 2 √3. One back both sides, knock yourself out, but don't worry about it.
But yeah, that seems to be okay. We're okay with that. And you guys should have a chance to practice that on the homework. So if I look at handout C, where the heck's handout C? Page 21, UV. Yeah, handout C, you'll have a chance to practice that for sure. I don't have the answers for us. I'll have to produce it over break. Yeah, but you have a chance to do that. So, okay, cool. So we're okay with part C? Whoops, great. Okay, examples 2 and 3 to wrap up part 3 of these notes. Give that equation, give the equation that rotates this an angle 3 pi over 4 counterclockwise. Don't overthink that one. It's really just this. Going counterclockwise, so it's all, you want to move kind of like
The positive direction, I suppose. Like you want to go this way, right? Going counterclockwise.
So what do you guys think I would do for this one? Don't overthink it. It's not that complicated. So theta, and what would I put next to theta? There you go. That's it. That's all you gotta do. Easy peasy. Yep. That's all you gotta do.
Wait, why is it?
Because remember, we're going counterclockwise in the positive direction.
Right. Yeah. So in order to so let's think about it this way.
So I'll draw it over here. So what if you wanted to move pi over 4 counterclockwise, right? So right now, I mean, just think about like what if you have like y equals sine theta? Theta and y. Obviously 0 is 0. Pi over 4 is √2/2. And pi over 2 would be 1. When we do, so now what you're doing is you're adding pi over 4 to each of these, right? So in order to get the same y coordinates, right? In order to get like y equals 0, you need to plug in pi over 4 for theta. So the starting point wouldn't be at 0, 0. Starting point would be pi over 4 times 0. When we do that transformation. So it's the same kind of thing that's happening that we do for rectangular coordinates. We do the same thing for the polar. So if you want to, so you want to basically start at a different place, right? It's starting 3 pi over 4 counterclockwise. So that's why you have to, I know it's minus, but you're actually technically adding it. You're going in that direction because that's a positive direction. Going counterclockwise. So just don't overthink it. Just go with it. So, all right. Next up, let's go back the other way. Let's go from rectangular to polar. Actually, I'm gonna have you guys try it. See what you guys get. I'll freeze the screen. See, so we're gonna go the other direction. So now you guys know how to convert for x. X is r cos theta. X squared plus y squared knows r squared, right? So you can kind of get a little creative here. I'm gonna do it too. Let me know if you guys want a little hint. All right. What do you got? Okay.
So the first step, I know it's not terribly obvious. Add x squared. Yeah, that squared is smart. I didn't know it, by the way. I looked in that. So I shouldn't take credit for it. So it does seem pretty smart, right? Because then you make that something you can use to factor out, right? So you get 4r squared. And then that's something you can factor. X squared plus 6x plus 9 is x plus 3 squared. Now, the one part you have to be a little mindful about is that I square rooted both sides here to get 2r equals x plus 3. Technically, it's plus or minus. So I am making an assumption that they're positive. So I am doing that assumption, just throwing it out there. But if I assume that okay, these are positive coordinates and great, then add to r cos theta, bring it, collect all between the r in it, back up r, and there you go.
That was going to, and that, of course, that's an ellipse, the original equation, the polar form, that's an ellipse as well. So you have a chance to practice and hand out C for homework or break. Okay, let's see how we can do part 4 of the notes. Any questions? No? Okay, I'll give you a chance to just copy it.
Wait, which part did you say? Took the root of yours if there's positive? Is it the x squared plus y squared?
Here.
Okay.
Yeah, so what I did was, at that point, I rooted both sides, and technically it's plus or minus, but I assume positive variables. So yeah, just make it easy for myself. So, all right, home stretch here, guys. All right, now let's just review rectangular stuff first, and then come back to polar. Okay, so just to review, when you have two curves, you want to see what the solutions are. You find where they intersect, right? So we want to know the points of intersection. So I'm going to graph y equals x squared. And y equals 2x. Let's do red for that one. So it's pretty obvious where they touch. 0, 0, and 2, 4. And you can also do it algebraic. Like, I know you guys can do that. This is kind of a joke for you guys. Actually, it's a total joke. I know you guys can do this. I'd be worried if you couldn't. Yeah, right. So there you go. Not hard. Okay, we're going to do the same for polar curves, though. We're going to find intersection polar curves in a similar fashion. Okay. So graphically, you see it, not hard. If you do the graph accurately, great. Algebraically, substitute, solve, not hard, right? So let's talk about how to find points of intersection for polar curves. Okay. So in this case, a physical point of intersection for the graphs of two polar curves does not necessarily indicate an actual unique point of intersection. So let's talk about that. A physical point of intersection for two polar curves can be one of the following. Is an actual point of intersection of two polar curves as unique in a specific indicated interval theta, fine. It can represent more than one point of intersection because these curves do repeat themselves, right? So it can represent more than one point of intersection of two polar curves in a specified indicated interval theta. Or it is not a point of intersection necessarily, even though, because there's no point in interval theta that can make both true. So that can happen too. Yes. Let's go through the examples. Mm-hmm. Repeat that one more time. Yeah, that's kind of weird, right? Because yeah, 'cause one of them would jump over, right? Yeah, so algebraically it doesn't confirm it, but thanks. But they are the same point physically, right? I think we would still consider it a point of intersection. But so let's do some examples because no, you asked a great question, but I wrapped my head around it too. So let's move on to the examples. All right. Yeah. But that's a great point that Catherine brought up because you do have those situations happening. So let's start with the first one here. R equals 1. R equals sine theta. Now R equals 1. Hopefully, if you guys remember, that's just a circle. And circle looks like this. Just like that, right? Radius of 1, right? Totally makes sense. So that's how that looks. Oh, wait. Hold on a sec. No, I lied. That was the other one. That was my bad. There we go. My apologies. It's just that. Sorry. I was doing the other one in my head. This one here, yes, that's also a circle. So that looks like this. There we go. That's what I meant to do. My apologies. Because a pi over 2 it is 1, but 0 it's 0, right? 3 pi over 2 it's -1, but it jumps over anyway. Okay, so clearly they intersect one place. One point of one physical, I'll say that one physical point of intersection, and that's going to be at 1 comma pi over 2. So we see that right from the graph. Go, Evie.
Will we ever need to worry about like the
We're going to talk about that. Okay. So algebraically, here's what I'm going to do, guys. Just going to substitute. Well, duh. We know this happens to pi over 2. So the answer is 1 comma pi over 2. So that's pretty easy. That was a real easy.
like, hey, here's a circle, R trace 1, here's R equals sine theta, that's less circle, but shorter radius, of course. That's good touch. Here we go, right? We're good.
Okay, let's get a little more crazy. Get a little more crazy here. Okay, 3 sine theta, yet another circle. The diameter is 3, mind you. The diameter is 3. So that one's going to look another circle again. Okay, so you got a circle there. No, they'll intersect twice. Yeah. There we go. Okay. This is going to be a limicon. Okay. So if we think about it, the inner loop. How long is the inner loop, guys? 1. How about the outer loop? 9, totally, right? And we're also going to be symmetric because sine about theta equals pi over 2. We'll be symmetric about that. Use a graphic calculator, totally fine. If you were to plug in, say, 0, I think you get 4. Is that right? Yeah. Plug in 0, you get 4. Plug in pi, you also get 4. And then it's going to look kind of like this. Okay. And it goes all the way down to 9. So let's count 2, 3, 4, 5, 6, 7, 8, 9. Okay, it's one of my better looking limicons. All right. Okay. So look at it. How many times do you think they're touching? I would probably say 3 times. Definitely 2 times. Yeah, definitely here and here. Let's. Yeah. Okay. So let's now try solving. So let me erase this so I need some space here. All right, so we're going to substitute. There's a 5 there, sorry. Okay, so that happens at pi over 6. Or 5 pi over 6. But technically speaking, it's 2 pi k plus 2 pi k because it could rotate again, right? So if you get the R values here, one sec. Yeah, so you should get pi over 6, comma, oh sorry, 3 halves, comma pi over 6. My bad. 3 halves. And also you should get, if you put in 5 pi over 6, also 3 halves. Okay. But interestingly, I'm not seeing 0, 0, right? What was it, sorry? Yeah, actually it probably would be, because if you plug in 0, you actually get 4 for R and 3 for the other. Yeah, because interesting, because graphically we're seeing that. Because 0, 0 is on this one. Yeah. Yeah, if you set this equal to 0. Whoops. Then 5 sine theta. So sine theta equals 4/5, which is somewhere around 90 degrees, but or close to 90 degrees. But yeah, I mean, so this is that example, that situation we we're talking about on the previous page, where a physical intersection could be one of the following. It is an actual point. So these are actual points. So these were actual. Well, so it's not a point of intersection because there's no point in interval that makes that polar equation true. So it's weird because it's physical. Yeah, definitely it's physical at 0, 0. But 0, 0 doesn't satisfy the first equation, obviously, right? So it's that last bullet point. So that can't happen. Algebraically, of course, so the actual points of intersection are going to be 3 halves comma pi over 6, 3 halves comma 5 pi over 6. Physically, we do see 0, 0, but in actuality, it's not. So it's just kind of a weird situation that's happening there. So just so you know, it's not an actual point of intersection. All right, let's keep moving. Let's go to example 4, guys. All right, example 4. Let me have you guys try that on your own. Okay, use Desmos or Precalculus to see where they touch, or see how the graphs look, and we'll talk about it after that. So once you guys try example 4, I'll freeze the screen. Yeah, you got 2 cardioids here, guys. You have 2 cardioids. Yeah, the cosine is going to be horizontal. The sine is going to be vertical.
Oh. It's like people who don't. Well, what I want to have is you can say it's I could. I might beat you in the toilet. Bro, no, you're gonna play that. And it's like you I hope Scary doesn't want to come out. What's I don't know, it's always in like started off with three. Sorry about people. I did the last guy. I think I beat the one minus root 2 on this cancel out. What's 1 minus root? I don't see one minus when you put in 7 power to 4, 1 minus 3 over 2. What is 1 minus? Is it root 2 over 2? What's one that says 1 minus root 2 over 2?
Okay, I'll give you guys a minute to simmer on that.
Bro, of course I was. I know it's.
Sorry, you need it. No.
Oh.
Not you.
Oh, he just put it as
Of
one
course I
minus.
would.
Okay. So there's 2 points of intersection that that are confirmed algebraically. Yeah, it looks like the touch at the pole also. So that's also another kind of weird situation that's not making sense for us right now. So we don't worry about that. But and it's actually I didn't draw the best way, but there's actually a point of intersection right there. At 1 minus root 2 root 2. Root 2 root 2 is about 0.7 something. So 1 minus 0.7 something about 0.3 something. So raise to 0.3 and 3 power 4. Actually, it's right. I'll have to do on the board. It's actually right here because 3 power 4 is right there, and it's a very small radius. It's like about 0.3, and then this is a bigger radius, it's about 1.7. 7 power 4, yeah, that makes sense. Okay, 7 power 4 between 1 and 2 radius. Yep, that makes sense.
Fake point 0, 0.
It's fake, yeah,
It's metaphor.
yeah, exactly.
Why don't you even like write that down on a text and just say like,
No, I just ask you, just give me the actual.
okay, so actual means.
Actual's algebraic.
Okay.
Right. I guess it's just more just a discussion topic. Like, hey, we see it's happening here, but algebraic's not confirmed. So. Right. Exactly. We don't care about that. Right. Okay. So again, hopefully that makes sense. When you cross off the ones, you want to get a little creative with your identities. Candidate is ranked 1. We know it's an power 4. And you understand. And it happens every second or third quadrant, so it's a rotation of 180, right? So 3 power 4, 7 power 4, go back 4 the other way. So, yeah. Okay. We're totally gonna get this done, so I'm really excited. Let's do 2 more examples, and we just ride off in the sunset for Thanksgiving break. All right. So again, same thing. Let's go and graph it. So the first one's a circle of a radius 3 halves, right? So it's gonna look, okay, that's a crappy looking circle. Just bear with me on that one. What's this other curve gonna be, guys? How many petals? And it's symmetric about theta equals 0 and length of 3. How many points of intersection you guys see right now? Totally 8. Okay, I do see no. Yeah, we do see 8. Yeah, we see 8 for sure. Yeah, totally. Yeah. Okay. Now let's do the algebraic stuff. So I think here, inverse cosine 1/2 is pi over 3. Or 2 theta would equal 5 pi over 3. So theta would equal pi over 6. Or theta would equal 5 pi over 6. However, if we're looking at from 0 to 2 pi, we could have also 7 pi over 6. 7 pi over 6 would make it true, right? Because then you get 7 pi over 3. The reason why is that because the 2 theta, right? Kind of weird.
So what if I, because
I would like move back around.
yeah, what 2 theta equals 7 pi over 3? That's true.
Yeah.
Because 7 pi over 3 is coterminal. So it's about coterminal angles, guys.
Okay.
7 pi over 3 is coterminal of that. So if you said 2 theta equals 7 pi over 7 pi over 6, that angle's within the first revolution.
Okay.
7 pi over 6 is in the third quadrant. And also 5 pi over 3, if I go around again, 11 pi over 3, no, sorry. Yeah, 11 pi over 3 is also coterminal of 5 pi over 3. 7 pi over 6, that would be in the fourth quadrant, right?
So does that, but if I go around again, now I've done more than one revolution, which doesn't make sense. So the answer is going to be, so in actuality, there's only 4 points of intersection. Physically, they're 8, but actual, there are 4. And all the points of intersection are going to be 3 halves, comma pi over 6, 3 halves, actual, physically and actual. Sorry, my handwriting stinks.
Physical on the graph is they're not expecting this to implement these like different. Like, looks like you know, no.
Yeah, I mean, but more so is because if I find out angles coterminals. You solve it, you get 7 pi over 6. 7 pi over 6 is another one that's coterminal. That's also so.
So what Catherine said, -3 pi over 2.
Yeah, so it's kind of weird again. And so to give you right here, guys.
We're working on 2 planes. What's real? What's actual?
Yeah, there we go. And that's going from 0 to 2 pi. So yeah, kind of weird how not, physically some don't show up algebraically. All right, last step. And then we're done. I would suggest that you square this one here. And then I'll let you guys try it.
problem.
Could we not just say like R squared equals R? Is that?
But we want to solve for theta though. She substitute.
Always.
And basically it's gonna look like this, guys.
Which is what's subtracting back. You're gonna remember that.
How do we know it's-
Because they are squared. You can kind of, well, the thing is, a cosine can't be more than one, right? So the most the R could be is one.
You get 0. Times 2. And V times 2.
Yeah, and actually the barbell should be a little bit lower. Yeah, let me think about this one here.
0.02.
Yeah, it's kind of a funny.
You can do 2 pi.
Am I still doing it?
Yeah, it should be a little. Shoot, the green curve I kind of drew a little crazy.
Oh, yo.
It's that, but it's not. It's not actually 0. It's pi over 2 0. 3 pi over 2 0.
Yeah, because 0 power 2 and 0 3 power 2 are actually the same thing. So it traces over it.
Wait, hold on. Yeah, if you, so even though it's not the same angle, because it fits algebraically, it still counts.
Right. Right. Still counts. Well, physically it is the same.
Well,
Because 0 power 2 and 0 3 power 2.
physically, it obviously is
They're
the
both at
same,
the pole.
but
so.
algebraically, it's also the same. So that's what makes
Yes.
it a true.
Right. 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 Because we're gonna go from 0 to 2 pi non-inclusive. Yeah. Yeah. Right.
Okay. Yes, because they both work algebraically.
Alrighty.
No.
So we get at what time? 10:55. Perfect. Didn't have to rush. If you guys want to get SR homework, you can, or just relax. Homework's the rest of the homework packet. I already put in Schoology. I'll stop the recording, save the video. We don't include it.